Welcome to Hydraulic Turbine R&D Laboratory, HRED IIT Roorkee. I am Mukesh Mangla, Chief of Laboratory. I'll be taking you around the laboratory and explaining you the procedure and the method for testing of hydraulic turbine models. You can see the reservoir which has a capacity of 300 meter cube, and on the top of it we have got a pump room which houses 4 pumps which are used to fill in the circuit. This laboratory was inaugurated on 10th of April 2018 by the Honorable Minister Sri Rajkumar Singh, who was at that time Minister of State for Power, New and Renewable Energy. This is the first independent laboratory in this region. This laboratory is accredited by NABL as per IEC 17025 2017, and the laboratory has got the accreditation for model testing as well as flow calibration. We are accredited for performing flow calibration of third party also. Here we can see the model. In this model, we have got an inlet pipe, which is a simulation of a small portion of penstock of the prototype. Then we have got this block, which houses the spiral casing, the guide vanes, the stay vanes, and the runner of force. On the top of it, you can see this, which is a guide bearing cum thrust bearing. This is the servo motor, and you can see the shaft. The coupling is in between the yellow portion, in which we have connected the turbine to the dynamometer at the top, which has a maximum capacity of 132 kilowatt. We can see the dynamometer, which is basically the generator cum motor. It is used as generator when we are testing model turbine, and it is used as motor when we test it as a pump. And on that side, we can see that we have got the VFD panel. That panel is used to change the speed as well as change the output to a standard value, and the output is fed back to the stay room. And you can see this is mounted on a trolley. The trolley can move in this direction as well as in this direction so that we can center and match with the model center line. So it's a very easy thing. It's all driven by the electrical motors. Here you can see a whirling rope. You can see if we hold a rope and rotate it like this, what would be the shape of the rope? This is an intrinsic phenomena of a Francis turbine and exists between a part load of 40 to 70%. Now we can see a straight rope. You can see the difference. Now the rope is straight instead of a whirling rope. This rope is formed at overload above 105 or 110% in Francis turbine. This is a high pressure tank, which is a simulation of a dam in actual powerhouse. Here we get the water from pumps below, which I will be showing you later. So the water comes here under a pressure. From that, the water will go to the model. This is a simulation of a dam in actual powerhouse. This is a low pressure tank, which is a simulation of tail race in the actual powerhouse, because we have a water which is coming out of the draft tube. Similarly, the water here is coming to this tank, and this tank is also used for cavitation test, where we simulate a different suction height in the powerhouse. The LP tank is movable on these screws in the X direction to take care of different lengths of the draft tube in the powerhouse. This is the HP tank, which can be moved in Y direction on this lead screw, and you can see this can be moved in vertical Z direction on this screw. So we have got all the 3 movements, 2 in HP tank and 1 in LP tank. Here we can see a Francis model runner. This type of runner is inside the model which we had seen earlier. Here you can see this model is kept upside down. Basically, in actual case, it is the other way around. To see the runner clearly, this has been put in this shape. The salient features of the laboratory are the maximum head is 60 meters, the maximum discharge is 907 liters per second, the capacity of the dynamometer is 132 kilowatt, and the maximum speed is 1600 RPM. These are driven by two motors which are basically 160 kilowatt each and driven by VFD motors. On the extreme top corner, we can see the 3D view of the laboratory. This is the list of the vendors which have participated in putting up this laboratory. Now we can see how the models are put on the test stand. Here you can see a Francis model and runner has been shown outside. Similarly, the orange one which you can see is a pump model and the runner has been shown outside. At the bottom, we can see the CFD analysis which is done in this laboratory. And on the other corner, we can see the hill curve, which is the final curve which is required by the customer. Here we can see the main pump, pump number 1 and pump number 2. These can be driven by the VFD motor and they can be run in parallel if a hard discharge is required for testing Kaplan or a low head Francis, whereas these can be run in series to get a high head for Pelton or a high head Francis. A single pump is enough for a mid-range Francis turbine. Here you can see the two VFD panels which are used for varying the speed of the motors which are driving the pumps. This is a special valve which is known as energy dissipating valve. This is used for testing pumps or pump turbine. This is a special feature of the laboratory and a pump cannot be tested unless we have a energy dissipating valve. Here we can see the flow meter, which is an electromagnetic flow meter of 350 mm. For accurate measurement, we must have a straight length upstream which is 15 times D and 5 times the downstream. This length ensures that the flow is through and it is smooth. We get an accurate flow. This is a panel for measurement of head. As it is well known that head and discharge are the main parameters which give us the input energy. And for head measurement, what is important is that proper purging should be done. So you can see different valves which have been put and a purging arrangement has been put there, but we can purge the different lines as the pressure varies from high pressure to almost full vacuum. So purging is a very important phenomena in measurement of pressure. Here we can see the calibration tank which is used for calibration of main measuring tank which is 45 tons. We can see that we have got weights by which we calibrate this tank of 2-ton load cell, where you can see a load cell at the top which is a tension type load cell. We calibrate this first by actual dead weights which are calibrated by the accredited laboratories, and then this tank is used for calibration of the main measuring tank. This is a measuring weight tank which is mounted on 3 load cells, 22 tons each. The capacity of this tank is 45 tons of water can be stored. This is used for flow calibration. We know the weight collected, the kg, the mass of the water collected and the time, so we know the actual flow. Here we can see the flow diverter which is used for diversion of water to the main measuring tank during the flow calibration. Normally the water keeps on flowing back to the reservoir, but when we want to calibrate, this flow diverter will divert the water to main measuring tank and we know the weight of water collected. When this is done, the clock is also automatically put on and off. We know the time of diversion, thus we know the actual flow calibration rate. This is precision 8-digit timer which is used during flow calibration and we get a very accurate time. This is put on by the sensor and put off by another sensor. So we know the exact time of diversion which is required for flow calibration. This is the arrangement for calibration of flow meters right from 100 millimeters to 300 mm, you can see various cones which we put to reduce the diameter and the sufficient straight length before and after is put. After this, the water goes to the tank which we have shown you earlier. Here we can see the different LT panels which are coming from the substation to the laboratory, and you can see from the size of the panel that so much power is required to run the laboratory. There are various panels which are put in here for transfer pumps, for transfer pump 1 and 2, 3, the main pumps, the dynamometer and the lighting of the laboratory.